Alright, today I'll be presenting a brief presentation on my literature server topic, which is processor and memory power optimization. So the outline of this presentation goes this way. So first we'll see what are the major power dissipation factors through the SoCs, and then next we'll look at some of the hardware optimization techniques, and as obvious the software optimization techniques, and then we'll conclude the presentation. So let's talk briefly about the power dissipation cost factors. So one of the major power dissipation cost factors is the dynamic power dissipation. So this is basically when the circuit switches back and forth, like when the circuit turns on and off. So that's a place where the power gets consumed. So that is known as the dynamic power dissipation. So most of the papers, like Atmos, states that this is the highest dissipation cost factor for any circuit. And then the second one is the static power. So whenever the circuit is not running any kind of logic, or you can say it as the circuit is in the standby mode or in the sleep mode, there will be some amount of power consumed by the circuit, which is known as the static power. And the second one is the short circuit. Short circuit is like let's take an example of an inverter. So inverter consists of p transistor and n transistor. When both of them turned on due to some abnormal reason, so there will be a huge amount of current flowing from VDD to ground. So that causes the short circuit power dissipation. And lastly, it's the leakage power. Leakage power generally occurs due to the subthreshold currents, which are unwanted. And then we'll see what are the software optimization techniques. So first one is the gate level dual threshold optimization. Second is the clock gating technique. Third is the DVFS, which is the dynamic voltage and frequency scaling. And fourth is 3D stacked DRAM. I mean use of 3D stacked DRAM. And the fifth is the memory partitioning technique. And some of the software optimization techniques are operation packing, and algorithm and source code optimization, and use of middleware. So let's see one by one about the hardware optimization. So gate level threshold optimization, basically it says that instead of using one threshold cell, you can use two threshold cells, like one with a higher threshold value and the one with the lower threshold value. So if you use two cells, using two level cells will decrease the power consumption by 50% according to a paper that I've gone through. So the diagram on the right is taken from that paper. So let's take a look on how this works and how the power can be reduced to around 50%. So let's take a design. Let's take any kind of RTL design. So you synthesize it using one type of cell, which is a high voltage, high threshold voltage cell, and then you do the static timing analysis. And then during the static timing analysis, there will be some kind of violations occurring. I mean the timing violations. So for each and every timing violation, based on its effect, you assign a cost function to it. So what you do is if the cost the cells which have the higher cost function will be targeted first, and they will be swapped with the SVT cell library. So the swap cell script helps in swapping the SVT library, and then again again you rerun the static timing analysis, so that finally you will get finally you end up with no timing violation, and at the end you can see like you decrease the power consumption by 50%. And then one of the major disadvantages of this paper is that the frequency of the operation is 500 megahertz, which is kind of too low for the present day, because most of the present day processor run at 2.4 gigahertz at minimum. So and the next technique is dynamic voltage and frequency scaling. So it's a mostly wide use technique. I mean it's even the old technique. So what this does is, so whenever the resources are limited, this will change the voltage or the frequency of the CPU. Let's say for example Intel has a turbo boost mode, which has which switches back and forth from highest frequency and lowest frequency based on the resources and some other constraints. And the next one is the clock gating. Clock gating is like you turn off some part of the circuit when it's not needed, and then you can turn it on when it's needed. So in that way you can save most amount of the power. So why do you actually need the clock gating? So let's say you're doing some reading operation from the memory. So reading operation continuously updates the register files, which requires power. So reading operation basically wastes lots of power. So instead of wasting the power, you can intelligently turn the register file off by using the clock gating. And then it will also be helpful when you have to limit the resource usage. And then this is an example taken from the internet. So let's say you have a CK represents the clock, and the EN represents the enable pin. So whenever you want to turn on some part of the circuit, you give EN1 so that clock and EN are synchron. So the clock will be supplied to the flip-flop which is present over here, uh, and uh, and the next thing is the use of 3D stack DRAM. DRAM is like 3D stack DRAMs are highly efficient, highly energy efficient, basically. So, and the major advantage of this 3D stack RAM is that you can place these 3D stack DRAMs close to GPU or CPU, so that there will be less memory. I mean, there will be low memory access latencies, and then the higher bandwidth. One of the major advantage of this 3D stack RAM is the higher bandwidth. So, and then one more thing to state at this point is that, so whenever you're transferring data from the memory to the you're transferring data from the memory to the computer, or from the computer to the memory. I mean, from ALU to the memory. So you have to, if you are not using a full bandwidth provided by the memory cell, so then it means that you are wasting a lot of power. So one of the papers which I've gone through is like typically uses an adjustable bandwidth, so that in order to reduce the loss of the powers. And then the final partitioning technique and the final hardware optimization technique is the memory partitioning. So basically, when you look back at 2 decades, so at that time the memory was like quite expensive, and the memory data size was the data storage by the memory was small. But nowadays the memory is quite inexpensive, and then it can store huge amounts of data. So the problem is that when you start storing huge amounts of data, there will be latencies when you are addressing the memory space. So that causes problem, and then more the latencies are, and then the more will be the power consumed by the memory. So one of the best ways is to do the memory partitioning. So let's talk about why you have to do the memory partitioning. It's like memory consumes about 60% of the total power according to a paper. And then there will be, as mentioned earlier, so larger memory increases larger memory access latency. So the basic idea is that you divide a large memory into a smaller chunks of memory, and then when you're using a particular part of and then this means it's low power, and then when you're using a particular part of memory, then all other memory units can be turned off, which means you're using less power and you're getting your work done. So in this way you can optimize the power. And talking about the software optimization technique, one of the technique is the operation packing. It's really amazing technique. So let's see how it works. So basically, most of the micro controllers these days come with a 64 bits, but however most of the softwares and most of the code runs in 32 bits. So which means that you're wasting a lot amount of lots of memory and lots of power. So instead of doing that, let's say you want to add like the two 32-bit numbers. So what you can do is you can pack two 32-bit numbers pack two 32-bit numbers at a time, and then you can do two additions using a single add instruction. So this is how it goes. So let's see, you have the operand 1 here and then the operand 2 here. So operand, and then there's for the first addition instruction, and then for the second addition instruction you have operand 1 and then operand 2. What you do is like you take this operand and you take this operand, and then you basically combine them into a 64-bit number so that you can add them. So and then this carry chain cut here is like, so for this part this result will be taken as a separate value, and then this result will be taken as a separate value. So this result will be the result generated by this will be a 32-bit number, and this will be again a 32-bit number. So you can do two addition operations using a single instruction, so which is quite interesting and quite efficient. And other software optimization techniques are the algorithm and source code optimization techniques. So algorithm, in the sense like you can optimize the code at a higher abstract level. It means that you can change, you can manipulate some of the logic so to consume less space in the memory, so that it consumes less power. Or you can do some of, or when you're talking about the source code, you can do some of the you can use some of the techniques like loop fusion, fission, and then you have the loop unrolling and loop merging and common sub expression elimination. So all these techniques are kind in a way helpful when you want to optimize the code and even the memory too. So but there are some optimization techniques which increases the memory size. I mean the code size, which are the loop unrolling. So you unroll the loops so that you increase the code, but they run quite efficiently and they consume less amount of power. But the price paid is in terms of the high code size. I mean larger code size. So and then one of the major thing to make sure is that you have to avoid the frequent memory access. So if you keep accessing the memory frequently, it means you're consuming a lot of power, so that the device gets dead in like few minutes. So and then another technique is like you convert the optimization, I mean the code optimization problem, into an integer linear programming problem, and then you can solve them by using some of the existing integer linear programming solvers. And talking about the middleware lies between lies below the application layer, and it provides functionality for the application layer. And then one of the best things you can do is you can collect the battery energy data. So it's like, so how much energy is got consumed by using some of the apps and something like that, and then you can store them in a queue, in any kind of format. And then you can use some of the machine learning techniques in order to process, like, so when the data has to be offloaded, or like when the data can be run on the phone. It's like when you offload the data consumes less amount of power, and so efficiently offloading and processing it on the mobile will actually help save the power. And then one of the best things is like when you offload it, you can actually downscale the voltage or the frequency, or based on the based on the machine learning output, you can actually adjust the voltage and the frequency settings for the energy saving, for good energy saving. So this diagram is taken from the paper 7. So what it does is this is the middleware. So runtime monitor keeps track of the battery data, so which will be fed back to the Q learning table, which is basically a machine learning algorithm. So what it does is based on the values of the output generated by the Q-learning table. So it determines when the data has to be offloaded, and what data has to be offloaded, and things like that. So and then it can, and the advantage of the middleware is that it can even control control the CPU settings like the voltage and the frequency, which is quite interesting. And then so this paper uses a Q-learning model, and it compares itself with some other existing and quite efficient models out there. So, and then when you see the graph, it's actually it's actually quite good when you use Q-learning, and it outperforms almost every of them except in some few cases, and in terms of the average energy saved. So, and the main takeaway of this literature survey is that there are only a few hardware techniques that can be done. So you can basically do the clock gating or DVFS, which are like only few, but there are much more software techniques which can be done. How like the code optimization and the use of the middleware. This seems to be simple, but they're quite powerful. And then thanks to the latest technologies which are giving out the 3D stack DRAMs, which are quite energy efficient, and some of the companies like Samsung uses some of the 3D stack DRAMs in their flagship phones. And then the one of the thing that I should talk about is about the memory optimization. So there has to be some other techniques to optimize the memory in order to save the power. And then lastly, I would like to talk about the compilers. So most of the compilers are not quite intelligent in terms of the compilation process. So there has to be changes made in the compilers so that they can optimize the code on their own instead of manually doing by it ourselves. So that's all about the presentation, and thank you for viewing it.